Hi, so welcome to lecture 3, and this lecture is about test effort assessment. So how do we know that the developers are doing a good job testing the software? This is essentially the topic of today. And okay, let's start first with backing away a little bit from the testing and to requirements. So perhaps you've seen the requirement pyramid before. So in the top, we have these fuzzy clouds. And these fuzzy clouds are the goals and needs of our customers. Those are, the ideas. And they are fuzzy because they can be implemented in many different ways, and they can, be different for different people also. And then we try to cover these, and we try to cover those in requirements, really. So on the level below it, we have some kind of features. For instance, like, okay, we have some kind of system with private information. So we want to make sure that only the authorized people get access to that information. So that could be a feature. So we could have a authorization feature, for instance. And maybe then we have, I guess we also have other features from other needs, like, okay, we need to have a shopping cart, or we need to have, if it's a web store we have, or if it's some other kind of system, we have other kinds of features. So these features then is or could be specified as use cases. So some of these features that interacts with the user, we could write use cases. And use cases is essentially a story who says, or a story of interaction between one of the roles and the system. So we have, here we have a use case, like user wants to get access to a restricted access. User requests access, system asks for credentials, user gives credentials, system verifies credentials and present restricted access. We also have an alternative scenario, because this is one use case where stuff can happen in different ways. So user gives invalid credential, system presents that credentials are invalid and you don't get access. But not all features are or is specified as use cases. Those could also be other forms of specification. We could have, lists of requirements, or we can have, just a short description of the feature or something like that. And maybe some features are not really interacted with in a way a use case is interacted with. But a use case can have different scenarios or different paths through it. So we have this main success scenario, the first one, and then we have an alternate scenario. So one use case can give different scenarios. And test cases are essentially scenarios with value. But not only that, we also have the system in a more concrete form. So when we're writing requirements, we are deliberately making the system a bit fuzzy. So we say, for instance, the user requests access here, and system asks for credentials. But system asking for credentials could be realized in many different ways, right? So it could be a console application where we input stuff into a console, or it could be a web application where we have a web form. Both of these implementations could implement the same kind of requirement, right? But when we're creating a test case for this, we are going to make it very, very specific to this particular implementation. And we're also making it very, very specific when it comes to input and output. So here, in order to create a test case for this, we need to specify, is this a web application with a web form? Or is this a console application? or some other kind of application. And we also need to specify how are we giving credentials. So system asks for credentials and user gives credentials. How does that happen? Is it a username and password? Is it just a secret passcode? Or is it, face recognition? Or, reading or scanning a thumb or something like that? All of these are possible implementations. Or is it a selection of these? So when we are writing test cases, we are going from this fuzzy thing, the fuzzy requirements, into something that is very, very much concrete. So we say exactly how should we input stuff here. We should put our thumb on a thumb reader, and we need to make sure that is the specific way of doing it. Or we are giving the password, and we actually should write out the password somehow, or what kind of yeah. Okay, so the use cases can have different scenarios, and each scenario here, like the main success one, which was the top one here, could have multiple test cases. So if we have, for the main success one, perhaps we have just a single scenario. So that could be this one with just a single single scenario with a single test case. So maybe let's create a valid user and try to log in with that user. So we created that kind of test case. But the alternative scenario here, user gives invalid credential, system presents that the credentials are invalid. That could well be many different test cases. So all the different ways we could be wrong, right? So we could have an existing user, but the wrong password or something like that, right? We could have an existing user, but no password at all. Or we could have a non-existent user and a correct password for some other user. We could have all these different ways of invalid logins that from a single scenario in the use case, we could create multiple test cases. So in order to see this picture, normally we are not writing it as a pyramid. Instead, we are writing it in a table form. I'm going to show it on a separate slide. Okay, other requirements could be requirements of how fast the system responds, so response time, for example, or something like that. So we could have these non-functional requirements, for instance, and those could also be connected to test cases themselves. But you can see over here, we also have test cases that are not really connected to any specific requirement. So these could be test cases that for instance, test the kind of technology that we're using, that we have selected. Maybe the technology stack is not a part of the requirement, but we have selected a technology stack, so we must make sure that stack works. So we could also have test cases for such things. Okay, so here are some of the scenarios that I made up for just an authentication system. So failed login without entering fields, failed login with only username, failed login with only password, failed login with wrong password but existing username, failed login with existing password but wrong username. And then we have the main success scenario here, successful login with correct username and password. And then I want to make sure that this technology-specific thing in a web browser works as it should, with session cookies and stuff like that. So I want to make sure that we're still logged in after reloading the application. And we want to make sure that if we resend the information, the login information, that we're still logged in. And if we open another browser window or another browser tab, we should be logged into that one also. I mean, we could have multiple or more scenarios than this. We could have, say that we want to make sure that if we have different roles, we could add more users, right? Okay, well, we want to make sure that an admin can log in. We want to make sure that a normal user can log in. So in order to see if we have covered all of these requirements, we could create this kind of requirement or test traceability matrix. And this picture is just from the Wikipedia page. And essentially, it's a table with all the requirements and the different scenarios within those. So you can see use case 1, scenario 1, 2, and 3. And then we have use case 2, scenario 1, 2, and then we have scenario or use case 2.3 and different scenarios of that one. Here we have the technical requirements, and essentially we have test cases on the y-axis here, and the x means that okay, this requirement is tested by this test case. But you can see that more test cases here are covering the same requirement. And we can see that this test case 115 also tests technical requirements. So it could be, multiple connections in this table. And then we have some statistics that it's just putting a number on how many test cases are covering a specific scenario or a specific requirement. And the other way around, they created this specific or statistics on how many requirements are covered from a specific test case. Normally, I would like to have a 1-1 relationship between test cases and a specific requirement, so that if we remove the requirement, we can remove all the test cases that belongs to it. We want to have this test case to requirement traceability, which was a goal of test cases. And this kind of table can create that. I have seen, and I think that one way of doing this would be to write test cases inside the issues of. So if you document your requirements as issues, you could also have the requirements or testing in these issues. That way, implementing the requirements and also testing the requirements could be put together. Not always a good idea, because issues, you want to say that, okay, we have now solved this issue. And if a test case is solved, so to speak, and not, and if it's a manual test case and we're going to do it again, we're going to recheck that manual test case, then we need to check all the issues that we've already closed. So look out for that. Okay, so then we had, that was highly connected to requirements, right? And this is the way we would do it if we're manually testing things. We would make sure that we have a manual test case for each requirement at least, or for each, But unit tests are more code-centric. So we write code that tests code and how to assess such things. So let's look at a Java project. Let's see if this one exists still. So Yoda time is an alternative date and time library for Java. And I found this when I was looking for projects with huge test suites. And this project has a lot of tests. You can see the different components or different packages here. One of these, the Yoda time, has 3,000 tests on it. We can see that all of those tests pass, and we can see that it took half a second. Oh, nice, right? This must be really, really good code here. Or I would say we don't know anything about how good this code is, because we have a lot of tests, and that says something, right? But we don't know how much code it is. If it's 10,000 functions, but we only have 3,000 tests, perhaps we're only testing 30%. Again, with 3,000 tests, doesn't look that promising or anymore. So we would need to have some kind of mechanics of saying this is tested good enough, and this is the topic of the rest of this lecture. So what we would say is, or I will define something called adequate tests. So an adequate test is that this is good enough. And this depends on the project. So you need to specify what good enough is for your project or for your particular component. And you need to decide that. So let's start with what I think or how I think of test, because I think this could help us in coming up with such a thing. So this cloud contains every possible program ever written in any language. So it's fuzzy, right? It's a cloud again. So here we have all the hello worlds, all the assignments you have ever solved, and all other code that's all other programmers have done. So millions and millions of different codes here. And then we have some codes are closer to the requirements or the specification or the thought out requirements that we have. And those codes, so to speak, that are closer to what we intended with our program would have some reliability. It solves some of the goals and requirements that we have created. And we call that reliability. And if you remember from the first lecture, so reliability was the probability that a random input would produce correct output for your program. So the green cloud here is, ways of solving this. So think of this as an assignment. So the things in the gray cloud are all the programs that, or the gray cloud around here are all the programs that does not even closely resemble this assignment. And then the green cloud are all the student submissions for that assignment. Make sense? All the buggy ones and all the correct ones. And then we can have, in the middle here, we have a collection of the correct ones. And I just want to warn you that thinking of correctness when it comes to software development is a trap. We're not really going to reach the green cloud here unless we are doing something like Hello World. For these super small, super simple programs, we can do it. We can also, for a bit larger programs, we can use this. Let's see from the first lecture, also see if I can remember it. Formal verification techniques to prove correctness. Or if we have so little input so that we can test, that means exhaustively test all inputs, then we can say that we are in the green cloud. But for almost any program, and especially if you have an input that is, a couple of integers or a string or something like that, then you will never know if you're in the correct one or not. So a test case is actually a constraint on the solution space. So I think of this as a line here that separates faulty solutions to correct ones. So a single test case would, remove some of the faulty ones. Everything that is not fulfilling or passing this test case is on the top left side of this line. And the correct ones must be fully on the bottom right of this test case. Those are all the programs that pass this test. So let's say that you have a program that should output, it should output the string hello world. So if you're creating a test case that just tests for that the output is a string at all, that we have a non-zero length string or something like that, then over here we have all the programs that are not outputting a non-zero string. And here we have all the programs that are outputting strings. But in order to capture what is correct, we should look deeper, right? We need to add more test cases, so to speak. So we add other test cases, and these are sort of creating more constraints on the solution space. And our goal is sort of to capture as tightly as possible the little green correct cloud, and to remove as many as possible of the incorrect solutions. So you can see this test here is a bit further away from the correct one, because its testing strength is not as strong as the other test that goes very closely. So it allows more incorrect versions with some reliability to pass. And actually, when we're creating test cases, this is the way tests look like. But we could also have these test cases that are redundant, and we talked a little bit about that the last lecture. So you can see if I create another test case out here, it will not help us in capturing the correct solutions better than the test cases that already exist. So this one here could be testing for a string, and this one here could be testing for a specific string, the hello world specific string. The more complex the solution space is, the more if statements you have, the more requirements you're implementing, the more complex this is. I mean, this is a grave simplification in 2D, right? So let's look at another simplification. And let's talk about our first criteria for, an adequate test, suite. So this first criteria, I've taken it from a book called Mathur, or the author is called Mathur. And you don't actually have that book, but you have my lecture. So I want you to think about this. So a test T for a program P with requirements R is considered adequate if each requirement in R there is at least one test in T that tests the correctness of P with respect to R. Such nice way of expressing oneself. This really means that if we have a requirement, we should have at least one test per requirement, right? So this is very similar to this thing, right? Or this, where we create traceability between requirements and tests. Okay, so let's imagine that I have requirement and the input domain of these, and over here I have output. So with one test case, I have one touching point between some input and some output. So if I add another test case, I have two different inputs and two different expected outputs. And I think I would, when I look at this in a graph or a 2D space, I would like to, if the program that I'm implementing is super simple, like this line, like this linear thing, then maybe two tests would be enough. Because the simplest way of implementing a line would just be the kx plus m formula, like y equals kx plus m. So in order to test that formula, so to speak, only two test cases would be enough, right? But do you agree? If the code is even simpler than that, if we have the hello world program, maybe just one test case would be enough. Is it outputting hello world to the console? If it does, it's correct. We know that because this implementation. If we have a bit more complex, we will need to add more test cases. So if the behavior is so simple, then two test cases. Is this enough? It depends on the complexity of the software. Maybe the actual software is like this, or the complexity is like this. So it's something more complex, or a graph going through this, or a spline going through this. A line such as this could be implemented with splines. So maybe I need to add another test case over here or something like that in order to make sure that we are actually testing this enough. So maybe 3 test cases for this a bit more complex line would be enough. So I think that this first criteria, saying that, okay, we have only one requirement only one test for a requirement, depends on how complex that requirement is, of course. So you might want to add more. So let's go to code a little bit closer to code. So this is a simple program. One, if x is bigger than 2, then we should throw an exception. And then we have a do while loop, and we increase x while x is less than 2. And then we return. And if I graph this, I can see that here we have 1. And from 1, we can go either to this line, throw new exception, or we start with the do while loop. So it's either going to 2 or the 3, the start of the do while loop. Or here is the x++, and here is the while condition. And if the while condition succeeds, then we go up here again. And then we output here. So for this particular program, we could do something called, or in order to make sure that we have tested this, we could create a different kind of adequacy criteria. And this one is a test T for a program P R is considered adequate if each path in P is traversed at least once. So in order to cover this with what's called path coverage, we could make sure that we have a test case that goes into this if statement and throws an exception. So we would need to send it, x equals 3 or something like that would be an adequate input. And the expected output would be that it catches, or that it throws an exception. And then we would need, another test case where we at least go through number 3, x++, which would mean that this criteria, this is if statement needs to fail. So perhaps a 1 or a 2 or something like that. So that I go down here. X++ would mean a 3, and then go up here again. So if I cover all these lines with my test cases, and I've covered them at least once, then I have path coverage. So this could be an idea. If I have if statements, I need to go in both ways in an if statement. So essentially, each if statement creates a or a division, or a jumping condition like the while here also creates this. Okay, so if I want to understand if I have coverage or path coverage, or then I need to use some kind of coverage tool. So there is this for Java code cover, for instance. So how do these tools work? Okay, they work with a technique called instrumentation. And I briefly mentioned it before, that if we have some code over here, and you can see that I've deliberately added a little bit of space here. So this is your code, and we want to know if this code runs, and if it completes something, then I can just log something. So I log to a log system, and I say that this method was called. And when we're instrumenting something, you take your program and you run it through an instrumentation tool. And this instrumentation tool looks like, okay, where are all the functions? Let's add more lines into these. And then we compile or we run them, right? So if I run this code, I will get this do connect into the log file. And then I can look, is do connect covered by our tests? Yes, it is, because we have this one. So we can understand, or we can look at if this function is covered or not. It might not be enough to look at the beginning of a program. We could also need to look at the end, or the beginning of a function. We could also need to log that we are going out of a function. So in this case, we see if do connect starts and if do connect stops. So this gives us a bit more granularity in our coverage, because we now know if this MySQL connect always throws an exception, for instance, we know that it was not fully executed. We did not fully cover this method. So if you think, or if you think of your code, maybe you have a lot of different statements in a single function, or a lot of different lines. So imagine you putting these log things between each thing that happens in your program. And then you also extract, you know, the small calculations that you do, like inside an if statement, you calculate if we're going to continue with this or not. And you create a log after each of these also. So you can look at each statement of your program and see if it was run during any test. And then we could look at this log, and then we can find out, oh, these were the lines that were covered, and these were the lines that were not covered. Yeah, and this is how it can look for some Java code when we run one of these tools. So we can see that, okay, print right header was fully run, and close was not run during any test, and then right body was run during a test, and then right file was not covered from any test. And this allows us to judge that, okay, we have some code not covered by any test. We need to add more tests. So we, as testers or developers, are given value from these code coverage tools. We can add now create new unit tests in order to cover this code also. Yeah, there are many different types of coverage. So if we talk about component coverage, means that at least one function in the entire component, this could be a library, this could be backend, or this could be a math component or something like that. At least one function in that component has been called during a test. That if that is our criteria of adequacy, I would not like to be the user of your system. But it could still be interesting, like, okay, we have 24 components, we have created the 24 different tests. And if each component is as simple as Hello World, then that would be adequate, right? So for these really, really simple cases. Then we could have class coverage a little bit better, a little bit higher granularity. We would have, okay, at least each class has been created, instantiated, and a function in that class has been called during a test. If we're, counting the constructor as a function, maybe it's enough to create one test case that creates objects of each class. Then we could have method coverage, and that is essentially this one, right? Where we, just log that every method has been called or not. And that is even better. And then we can have block coverage. And a block is a piece of code that is always executed together. So block coverage, so if we look at, not sure if we can look at these parts of code. Maybe I need to go back. Yeah, so, okay. So this throw new exception, when we call that or when we run that, we are going to get thrown out of this function. But this x++ and this while condition here is always going to be executed together. You cannot jump out of the program in between these two, unless we have something like an integer overflow or something like that, and that causes an error. So we could group x++ and this while loop together. They are always executed. But the x++ and the return statement is not always executed together, because there are cases where we are going to continue the while loop with another x++. Do you understand? So a block coverage is taking different blocks of code that are sort of guaranteed to always run together. I was not using these lines of code because when let's see, this first one here, file input stream, when I send it a file, it probably can throw an exception. This means that I cannot group this one with the lines after it, because sometimes this will throw an exception and the execution will end there. However, I think output stream out and sock get output stream and int byte read. These two will always execute together. And then we have this while loop, and probably these needs to be separated because sometimes we are receiving a -1 and sometimes we're going to continue. So a block statement are connected things that are always going to execute together, like 3 and 4 are always going to run together here in this graph, because there is no way out of 3 that cannot happen. So for block here, for this graph, we have one block here, the green block, and since it has 2 ways out, it creates 2 different blocks here with 2, and then 3 and 4 are executed together, and then we have a separate block number 5. And then we have statement coverage, and statement coverage is every individual thing that can happen. Sort of, it's almost like instruction coverage, where if you know that the source code that we write are really put down into small instructions, like the add instruction or the mul instruction or something like that in the processor. So if we're dividing down the language into its smallest parts, so to speak, then we can have statement coverage. And this normally is what we measure, for instance, in Java. So they have this bytecode, and inside the bytecode there are different statements, and then they put these instrumentation log things in between each of these statements, and therefore they can look at, okay, these statements were run and not these other things. Okay, so that is sort of the highest granularity. One could argue that it saves more time with block coverage. Okay, when I'm running my test suite and I have all of these logs here that happens all the time, what happens to the execution speed of your program when you introduced more code? And these logs, maybe they're not really writing to a log file, maybe they are writing to memory. But what happens? Running your program, does it go faster? Trick question. It goes slower, right? So since it goes slower, maybe some of the bugs that depend on runtime or speed will not show up when you're doing this thing. Just to let you know, and it will let your test take longer time. It's actually quite fast normally, just to if we can write to memory at least. Okay, loop coverage says this. But before we had this path coverage, and with just one test case, we could cover the entire path of the previous code, right? So just to make sure that we go up here once at least, and then with loop coverage, we go a little bit deeper. We also say that I want to go through each loop 0 times, 1 time, and more than 1 time. So I need to have one test case that does not go through the loop at all, if possible. And let's see, with a do while loop, that cannot happen. So 0 times means that we go do this one once and then exit the first time, right? And then 1 time would be that we go do this and do it again, so 2 times. And 2 times would actually mean that we're running x++ 3 times. So in order to get loop coverage, it's actually quite important, I think, to get loop coverage, because we want to make sure that if we have different ways of running our code, we want to capture all of these ways of running the code. However, please note that for some codes, loop coverage can never happen. So I have a piece of source code on our later slide where we're going to look at this. Okay, decision coverage means that we're going into different decisions. So every decision is sort of made both ways. So if I have an if statement here, I will go both ways in that if statement. There is a good source of coverage, and I want you to take a look at this one, because it will tell you a lot about different types of coverage. Not maybe the book is not going so deep through this, so please open this one and go through this one. Yeah, so a decision coverage, you can read more in depth in this. I think I will just confuse you if we go into this. There is something called MCDC down here. And this MCDC is sort of, we make sure that we take every possible path through the program. And we also make sure that if there is a decision made in the program, sort of an if statement, we take those decisions for all possible reasons that we can take those decisions. So if we have two booleans, for instance, and we say that this boolean and this boolean or this other boolean must happen for us to go into it, then we need to go into the if statement for the reason of the first boolean being true and for the reason of the second boolean being true. So if you have more complex boolean expressions, then you need to have a lot of different test cases. And this has been, let's look at this line here. This metric is specified for safety critical aviation software. Like, okay, so if you're writing, a flight system for airplanes or something like that, then you probably will need to show that you have this MCDC coverage for your code. So there are these different standards for testing. I'm actually not going so deep into this because I think they are pretty boring, and they're very specific to the different domains that you come out to, right? Okay, so open this link and look into the types of coverage. Yes. Okay, so here is the code where I got a loop coverage that did not, that could not happen. So here you can see that I have a piece of Java code. It's for a web server that I wrote. And you can see up here, I have this enum, and it has a lot of different things in the enum. And down here, I'm using the enum, and I have a for loop. And I'm going through the different values in the header. Problem is, when I run a coverage tool, you can see that I get 100% statement coverage, 100% branch coverage. So I'm going through all of the different ways, right? But I only get 66% loop coverage for the header class. And the reason for that is that since this don't allow me to go through the loop, 0 time or 1 time, I cannot get full coverage. So actually, going through this loop less time than I have in my enum up here doesn't make sense. So this is sort of a measurement error. I'm unable to measure the coverage of this one correctly with the kind of instrumentation that I have. And I think this exemplifies one of the problems with all of the different techniques here, that the way that we measure things does not always show the entire truth. And actually, this is the case for all measuring, all software measuring, and the reason that we humans are actually needed in making decisions still. So if you think of a simple thing like measuring the height of me, and then you're measuring the height of me with me drawing a line on the whiteboard behind me or something like that, and then we measure that with a ruler or something like that, we're going to get measurement errors, right? So with every way of measuring things, we're going to get a measuring error, and this actually is a measurement error. So if we decide that we need to have loop coverage here, we need to be able to, in order to test this code fully, we need to be able to mock this HTTP header and replace it with something that does not have headers in it. And then we could reach 100% loop coverage. But that test, I would argue, is not needed, because this will never happen, because we, in HTTP headers, we're not going to get fewer of them. Probably can get more of them if we're going into later versions of HTTP than we are covering here. So I've found out when trying out these different kinds of tools that for path and loop coverage, this can sometimes happen. Path coverage, actually, if you have an if statement, I think we could look at this code again. So if you have an if statement here, x bigger than 2, what if I have another if statement that happens before this code that also checks that x is bigger than 2, or that checks that x is less than 2? So that would mean that some code will never happen. Right? So if you already checked something and then you recheck it, then you will get dead code. And you probably know that the IDEs today can detect some dead code, but not always. So if code is executed together with other tests, then we can get this unreachable coverage, I call it. Error handling code can sometimes be like this also, because the way that the code is written, a specific type of error cannot happen. It's just, we have written code, so it cannot happen. So I found that, and especially in Java, which forces us to handle exceptions, even if they really cannot happen, then we can get this unreachable coverage. That means that we're writing error handling code that cannot happen. The catch things can never happen. So we're really just making it hard. And the coverage tools that we have cannot help us here. They are actually, if my boss is looking at my coverage report and then deciding my salary, they are doing me an injustice because of the measurement error in this one. So factory code, I've also found that sometimes when you're creating objects, so factory codes are really classes that create objects, and sometimes you cannot create objects. You cannot run these, because when you create these objects, actually things happen. So databases are, created. It's sometimes because we have hard-coded dependencies and stuff like that, and sometimes for other reasons. Maybe we don't want to create this self-destructing AI code, or I don't know, or whatever it can be. So factory code, I found also can be helpful. In some frameworks, I think this is solved in the later versions of JUnit. So maybe we cannot run the main function. Maybe we cannot test index.js, just because when we run that file, everything happens. The entire program starts. And maybe it starts to communicate with the internet, and all this shit happens. So maybe we cannot run it. But in JUnit was just the case that you could not start it at all. So in order to start the program from a unit test, you need to create a separate process and then start it within that process and then monitor that process and stuff like that. But then I could not get coverage for that thing. We had this double checks and things like that. But I have been speaking for 45 minutes, and let's have a 15-minute break. So 20 past 10. Continue. Okay, so let's continue. We talked about coverage and that not always possible to get coverage, even if it's usually very usable. So more things that is hard to show coverage for, and I think this is slightly connected to stuff that is, you know, harder to test. So if we have a lot of resources that we need in order to test it in a file system or databases or over an API or over network or something like that, then usually this makes your code also hard to show coverage for. So I mean, if dependencies really make stuff harder. And the reasons for this is, you know, if we're going to start up a database, for instance, then we need time, and we need access, and we need to configure and things like that. I would say that coverage is mostly usable for your unit tests, and not for the bigger tests, not for integration testing, not when you're really using the file system or running system tests and stuff like that, to my experience, at least. Sometimes in databases, we also have code in the databases. So we can have views in the databases, and these contain rules for how data may be stored and stuff like that. So we don't get coverage for such rules from the coverage tools connected to your unit tests. So if you run your code on a specific hardware, like an Arduino or Raspberry Pi 2040 or something like that, a normal Raspberry Pi, Pi 4 or Pi 5 or something like that is not a problem. But when you have specific hardware where this run on microcontroller, then you might not be able to test the code with coverage. And maybe you cannot really run your code unless you have this microcontroller, if you have specific microcontroller dependent code either. So for such applications, you need to do other things. Either you need to simulate, and you can sort of show coverage in the simulator. But to my experience, those simulators usually don't allow us to run coverage tools, or the coverage tools are not made for those simulators either. So I've had problems with this. Sometimes when you're working with specific hardware, you also need, I mean, the output is really current going through some diode or something like that. So an LED is lighting up. And this makes it hard to automate testing of it. Of course, it can, in many cases, can be done still, but it would require specific hardware. So in order to test hardware, you're usually creating these testing rigs in hardware. So if you have something very machine specific, either simulation, or you do this, you create a testing rig where you above a LED, you have a LED receiver, and then you can, test that the LED starts up, right? Real input is also difficult. So if you have, a steering wheel, or even something like a mouse can be hard to get the real input for, or if you have these sensors and they have very specific inputs, this makes stuff hard to test and also hard to show coverage for. If you have multiple languages in the same application, and maybe you don't think of a regular expression as a separate language, but it is. So if you have a regular expression and you want to try to, find all the paths through the regular expression, that I've not seen any coverage tool handle. So normally I would test a regular expression separately in this, reg editor or something like that, and I create a number of test cases there. And then the function that is using this regular expression, perhaps if we can dependency inject a simpler regular expression into that thing, we can test that separately, and then we test the regular expression in this specific tool for that. Lua is a scripting language for games and for home automation and a lot of different things. So if you have a basic or a programming language, and then you have another programming language, and you run scripts in that language, suddenly your code is not only in Java, for instance, or in JavaScript, it's also in Lua, and the coverage tools usually don't handle both. So if you have these cases, I would suggest that you create tests in Lua for the Lua code, so that you can use the Lua tools for those. There are, of course, other kinds of scripting languages. So whenever you think that, oh, we might need to introduce a second language as a scripting language for some reason, I would advise you to think about how you should test those script things and the real reason that you want these script things. I would, if I could, stay within one language, not having anything scripted. I mean, we could have Java. Let's talk the Java world. We could have a part of the Java program that is sort of the script that someone else writes as script that compiles. When you start up your program, you compile this Java program, and when you change the script, so to speak, you will recompile those Java program and you dynamically load them again, and you can get that working. I think that would probably be a better solution than to introduce a second language, unless you have a test strategy for that language. Similarly, if we have data-driven code, this might also be very hard to test and hard to show coverage for, because we get so many different possibilities, and it's hard to test for those possibilities. So in the effort to make my code super dry, when you make your code super dry, eventually you will end up with a domain-specific language in a JSON file, or an XML file was the format that we were using at the time. That sort of, you change everything in this one. I think the YAML files are this thing today, where you configure everything in the YAML file. And so your code is really data-driven and being put together using these YAML files. And this creates a complexity that is super hard to test. So we would like to test all the different possible YAML files, really, and how our code interacts with those. I've also seen some iterative or recursive functions when I've been programming my share of simulations, physics simulations, or simulations of hardware and stuff like that, and computer games and neural nets and stuff like that. These things are also where creating code that is really hard to understand, really fully understand the output from, and the connection between the input and output in a neural net is quite complex. So I think that tests are still really, really good, but it's hard to understand if we have tested enough. I think that one of the problems with today's coding, when we are introducing LLMs into our programs, and we are by API calling them, and we want to find out if we can solve this problem with an LLM. So I've for instance, extracted pieces of text from a bigger text and then send it to the LLM and ask it through a prompt, does this text contain a curse word, for instance? And then you answer yes or no, and then I get code back. And of course, I can test my own code, but if I want to test my own code in conjunction or with the LLM code, then I have a bigger problem. I think that we can do it, and I've done it like this. We want to have enough test cases so you can create a reliability of that code, how reliable it is, and how many cases it does not produce correct output. So that is the way I've done such things. But more complex code is more complex to test, really. And data-driven code, or when you have multiple languages, or you have these simulation or recursive functions and stuff like that, is not always as easy to test. Sometimes we need to test specifically for these things, and testing a little is always better than not testing it at all. For simulation, for physics simulation, I've tested all the units, so to speak, successfully, but it's hard to test the entire simulation. Okay. Okay, sometimes during assignment 1, part 2, you will probably realize that you have private methods. And these private methods, sometimes in some test frameworks, in some languages, you're allowed to write unit tests for these private methods. In other frameworks, you're not allowed to call them. You cannot call on a private method itself. So we can have from test unreachable interfaces that we would like to test. So one solution would be to open up the visibility of the function. So you say that, oh, this function is no longer private, it's public. And now I can test it. But then we will lose the idea of encapsulation and the idea of writing object-oriented code in that way. Another solution that I've seen is, okay, we make stuff protected, so it's reachable from a subclass. And then we inherit a test class that can allow input into these methods that was previously private. And a third solution is that we open up the language, and for Java, for PHP, for C#, I've seen this where you can open up a language where you can take an object and you can say, okay, this object has these methods. Some of these are protected or private, but we can still call them through this specific these specific ways of doing it. I don't remember the word for it. If someone has the word, please tell me. But you can sort of look at an introspection or something like that. I think these tools are used where you can inspect objects and call them. I'm sure it can be done on JavaScript also. But the problem is that we say that you should not call this function, but then we would like to call them still, right? And my advice would be that if you run into this case, usually a better solution is to divide the class into an inner class and an outer class, so to speak. So I had a case where I had social security number, and on the inside of social security number, I was working with this array of characters, the array of characters was like number, either dash or a plus, and then a number if it's a Swedish security number. And then I had these private functions handling this array and making sure that all the numbers were correct and making sure that I could extract, a section of this, because I wanted to know the year of birth or the day of birth or just the security code in the end or something like that. Makes sense? And then in order to test these private functions, I extracted a second class, which I called numerical string. So that I had the first 6 numbers was one numerical string, and then the 4 other numbers was one numerical string. And suddenly I can, manipulate that part of the code separately from the social security number. And in this case, I can dependency inject a number string into the social security numbers constructor, and now I can test the previous private methods were now public in numerical string instead. Yeah, okay. I've also found that for some, in this case Java, the console was unmockable, so we could not mock the console itself. We needed to find other solutions. But in those cases, we can wrap the classes, or we can create an adapter around the classes, and we can test your code using that instead. Yes. So when inspecting, let's see, if we go from the beginning again. When inspecting this Yoda time, I found out that I ran coverage tools on this one in order to inspect all the 3,000 test cases of Yoda time package. And I found out that they had a fair coverage, but then I found out that some tests that created coverage did not contain any asserts. Think of this. If I don't assert anything in a test, what is the value of the test? Is there any value? I run the code, it ran, but it didn't assert anything. I did not compare an actual and an expected output. Some value it is, because we know that it ran and it didn't crash, right? And from the first lecture, let's go back to this one. You may remember smoke testing. And smoke testing, we just see if it crashes or not, right? So yeah, so there is some value in this, but perhaps a smoke test should not be mixed with your unit test when measuring code coverage. So you should have a separate test suite for such tests, and perhaps your integration tests that that is part of another thing also should not be a part of your unit test. So have different suites for these. So smoke tests usually don't have any asserts, no condition. We were just looking for crashes, or we're looking for 100% CPU and stuff like that. But in some cases, there are asserts, but in the code. I call these in-code asserts, and they are sometimes called invariants, where you have functions that in your class that make sure that the state of the class is not an invalid state, that you're not in an error state in the class. So you create usually a private function called invariant in your class, and that class just checks that every variable within the class is within the normal parameters. So if you have a password class, for instance, in your invariant function, you would check that the password is longer than 10 characters, if that is your rule, and that it contains numbers and characters or something like that, if those are the rules that you have for a successful password, so to speak. And imagine that you have this invariant function now that contains all the rules for this class. You can run it in the constructor, and you can run it in every function that changes the state of this. So after you change the state, you run the invariant. And if you change it to an error state, the invariant will have an assert within it, and that will make the program crash if you run into an error state, right? And this may look scary, but it's actually a good idea that we actually crash the program if we get into an error state, so that we never sort of allow a program with bugs in it that creates error states to pollute our system. The only problem is that these crashes should only happen during testing. But perhaps in some cases it's better that we crash during production than to get into the error state. If it's a lot of money, and we find some way of transferring this money to someone's account that is not valid, perhaps it's better to crash the bank software than to actually do the transactions. I don't know. It's from case to case, of course. But if you have these invariants, suddenly your smoke testing becomes much more powerful. Right, so imagine that every class has these invariant functions that make sure that we don't get into an error state. Suddenly your random testing or your smoke testing becomes more powerful, because we now have a lot of different asserts in the code. there are a number of different things or that I think is helpful here. Something called design by contract and defensive programming. And I think this invariant thing is a part of defensive programming that they are using this. And you can look into these two things. This dynamic type safety is a PHP thing, and I think we can sort of skip that now. So here is a test of, or a smoke test. So imagine you find this test case among the other unit tests. So maybe you want to exclude this test from your code coverage measurement. I have actually found it useful to sometimes create tests that don't have asserts in them. But those tests need to rely on another mechanism. So in my code, I usually create a constructor, and in the constructor, I have the invariant. That means that if you send proper arguments to the constructor, you get an object. If you don't send proper arguments or invalid arguments to the constructor, you get an exception thrown. And this means that in order to test such a constructor, of course I send a lot of different erroneous arguments to it and make sure that an exception is thrown, right? So you can see on the right here, a constructor should throw exception with no parameter. I call the die class with a null, and it should fail. So this is a way of testing that if the ability of testing exceptions is not in the testing framework. But I might need to have another test case that complements this test case where I actually send the correct data. So here in this one, should not throw an exception on proper argument. So here I create a new die and I send a random object into it. And this one does not have an assert in it because it should not throw an exception. Make sense? So we can have complementary, I call this complementary negative tests that show value, but they are only valuable when they are in the combination of this other test. On their own, they seldom have value. But if I have a number of these tests where we test for different test exceptions, then we get value from our complementary tests. Okay. So let's talk about other ways than coverage to evaluate your test suite. And there is something called mutation score. And mutation score works in a similar way than CS quiz that you're using for assignment 1, part 1. So in CS quiz, you have one version of the system code that you have access to, that you can, change and do, change to your way. And then I have a number of versions of the system that I run your test suites against. I have a correct version of the system that I run your test suites on. And your test suite should pass the correct version of the system. Otherwise, you have a test that fails. If you have a test that fails the correct version, then we have a problem in the test suite. But we also have versions of the system that are buggy. So I've manually created a number of different bugs, perhaps with, sending a null array or something like that. And then I run your test suite against those, and you should catch those by at least one test should fail per buggy version. Mutation score works in a similar way. So mutation testing seeds artificial defects, so-called mutations, into a program. And this is not super complex. We just look at the code that you have in your system, and we take an instruction in your code, for instance, an if statement, and we replace whatever's in the if statement, if it says like x less than 2 or something like that, and we just change this less than to a bigger than. That would create a mutation, a defect, a bug has now been introduced, and we run your test suite against this one. If your test suite finds the bug, then we kill the mutant. And that is a good thing, right? If your test suite does not find this bug, then your test suite is weaker than a test suite that would find the bug. Make sense? So we want test suites that are strong in finding bugs. And mutation testing creates a lot of different versions of the system and changes a lot of different instructions. And then we run the test suites over and over on these different mutants. And we count how many of these mutants you catch. We actually measures the test suite's ability to differentiate between the implementation and other mutated implementations. This is sort of problematic in many ways, but it's actually a quite good indicator of the good test suites if you run a test suite. There is a problem called equivalent implementations. And that sort of means that what if the mutant is correct still? What if the mutant doesn't matter? Mutation doesn't matter. Then we have another correct version of the system instead of a buggy version of the system. And this actually happens a lot. But let's take a look at some code. So we have input equals 5 here, and then we call some code here, and then now this is a test. So we have input 5, we call the function on the input, and we assert that it should throw an exception. So and then we have the original code that I wrote, so to speak, or that you wrote, right? Your system code. And we just run the test on this code. So input is 5. That will mean that input is over 4, right? So we're going to get an exception. The exception is going to be thrown, which is OK. Here we catch the exception. That means that it's OK. If the exception was not thrown, then this assert fail would be called, and then the test would fail. Makes sense. So the test and the implementation are now aligned with each other. So the test pass this implementation. We now create a mutation where we change the bigger than to a less than. And we run the test suite again on that one. So we input 5, and then we call the function on input. And now 5 is not less than 4, right? So we're not going into this. We're not going to be able to throw an exception. That means that assert fail is called, and that is a good thing. We now killed that mutant. We found the bug by test. Let's look at the another mutant of this one. We did change the bigger to a bigger or equal than. Send it to 5 again. 5 is bigger or equal to 4, which means that we're going to throw an exception. And we're going to catch the exception, which is OK, which means that we did not kill this mutant. This is an equivalent mutant to this implementation. But the problem is like this. It's just equivalent to the test suite here. If I had sending a 4 here, we don't know what would happen, right? This is the input that should be here is 4, and perhaps also we should have another input which is 3 that doesn't throw, a complementary negative test that does not throw in order to get it stronger. So this one, now we have for this input equivalent implementation that does not throw. And when we calculate the mutation score for these two, we now have found 50% of the mutations by testing. It's your mutation score. If we add another test case, this one, this is a true equivalent implementation of this one up here. Because for any input, this one and this one is going to work the same, right? They are truly equivalent. So if I is 3, then they're going to not throw, right? Hang on a second. I'm making a mistake with the 4, right? If it's 4, they're not going to throw. If it's 5, they are going to throw. So if it's 6, they are going to throw. So they are working exactly the same. So, and this one you're never going to be able to detect. This one is actually a good thing that we did. I think that this one is a true mutant that we did not catch. Okay. There is another technique, and this is a bit more complex, that we can evaluate our tests with. And 2012 or something like that, I was starting out as a master student, and I wanted to find some interesting thing to solve. And I've been looking into this code coverage thing, and I was not, satisfied with the mutation score, and I was not satisfied with normal coverage either. And I found a technique called dynamic slicing. And dynamic slicing means that we can single out instructions that affect other instructions. So if we look at this code over here, x equals 5, and then we print the value of x, and then we change the value of x, and then we go into this if statement, if y is bigger than x, and then we change the value of x again, and then we return. And some of these values affect the value of what is getting returned, and some don't. So this line up here affects it, right? This line here does not affect it. These lines affect, and this line return also affect what gets returned. This means that this print statement is not actually tested here, because we don't look at the console or system out. We're just testing the number, right? So this line here is not really tested by this test case. And dynamic slicing lets us calculate a dynamic slice of a run, where we can look at which lines of code did affect a specific result, and then we just input whatever is in the assert. This 4, why do we have the value actual here? And we calculate which line are affecting that result in the system. And then we can compare those lines to all the lines in the system. So we run this on every test, and we can see which lines of code in your system are really covered, are really used by any test case in order to assert anything. This is quite an interesting technique, and for some cases, this can be useful. I didn't know, but a German guy, David, I think it was called, implemented this checked coverage at the same time as I was working on it. Here is a link to his paper on it, if I remember correctly. Problem is you cannot assert things that did not happen, and some problems like file, database, and other languages and stuff like that are still not coverageable. But I did a little bit of an experiment with checked coverage and mutation score and normal coverage. So this is a view of code that is different instructions. So every X pixel here in this picture is an instruction in the program. And there are several different classes. So we have a vector class here, and we have a triangle class. And when I run a test, the white areas here are instructions that are executed during that test. That is, line coverage. Actually, I don't fully remember what the yellow is right there, but the red and blue is when I run mutants on this. So if a mutation here causes a crash, or a mutation here causes an exception, then we're sort of capturing these. But the green stuff here is checked coverage, where I run the code, and we've the instruction at this position was actually used and asserted on. that this calculation happened, and then we asserted on it. And then I created a test suite that I thought was, you know, really thoroughly testing these classes. So we can see that I did not mock the vector class here when I tested this triangle tester. So we can see that these first instructions here are not really used in the calculation of the value that I'm asserting, but these instructions are, and these instructions are, and these instructions are. So if I can find parts of my program that is never used in any test, so we look at these tops here, they are run during tests. So either we have line coverage or statement coverage, but they are never, you know, used in any green here, which means that these are lines that I should add tests for. Or this could be lines that doesn't matter for anything. So perhaps it's console log for something like a debug thing. Never really. We can also see, interestingly enough, that they never crash for mutation score either. So even if we, you know, mutate the code there, it doesn't crash. Yeah. Okay, finally, and the last thing of this lecture is like this. So Kent Beck, who wrote this TDD book, or the test-driven development book, more or less says that, okay, if you don't get good coverage, and by good coverage, it's like, you know, 90% plus, then you have not designed your tests good enough. So if you remember how to design tests in TDD, you need to write the test before the implementation, and the test should fail before the implementation runs, right? So we get to red first. And then you change the system a little bit, not too much, a little bit. And you don't introduce anything into the system that is not covered in your test. You just pass that test. And then you run it again, and you're in green now. Now you know that for every line of code that you introduced, you have changed from red to green, which means there is a test covering that line. So test-driven development, according to my experience and according to the book, gives this super nice coverage, not only for statement coverage or things like that, but it gives good coverage even for this mutation score and for this checked coverage. So, but it takes this sort of painstakingly process of TDD in order to get there. And I think that most programmers out there will not use TDD in that way that you're doing it in assignment 1, part 2. Usually they are introducing tests on another level where they are, you know, integration testing something there, or they're just testing the backend, and they are Postman and writing testing Postman for the entire backend, for instance, and they call that test-driven development because they write test first. So there is something called test first, but this is not the same thing as TDD. Okay. There is some TDD code on the homepage, and we are done. Thank you for listening, and good work.